Hello, this is Pangborn. I'll be presenting this paper titled Hierarchical Hybrid MPC for Management of Distributed Phase Change Thermal Energy Storage. If we look at historic trends for vehicles, as well as predicted future behavior, one of the things we see is that the amount of electrical power on board vehicles is dramatically increasing. If you look at the plot in the middle of this slide, we see that for the case of aircraft, there's an exponential increase in the amount of electrical power on board. I'll note that this y-axis here is logarithmic. This is true not just for aircraft, but for a number of vehicles. We've seen it, of course, in consumer automobiles, cars like Teslas, but also in on- and off-road vehicles and naval ships, where electrified systems are more efficient, more environmentally friendly, can have increased productivity, but also, as a result of having more electrical energy on board, also generate a lot more thermal energy due to inefficiencies. And this is posing a huge challenge to thermal management, where dissipating this energy that's generated, perhaps storing it on board until it can be dissipated, is becoming very challenging for these systems. One of the solutions that can help to address this is using latent thermal energy storage to improve power or perhaps energy density. Most of the previous work looking at this has focused on buildings, where one might take a tank of water and freeze it or melt it as a source of phase change thermal energy storage. However, there are also studies that show that we can use phase change materials in vehicles, for example, paraffin wax, in order to improve thermal management. That's been shown for batteries and power electronics, where particularly under pulsed or intermittent loading, as shown here, we can use thermal energy storage as a sort of buffer to reduce the transients that hit our heat rejection system. And what that allows us to do is downsize that heat rejection system such that the total mass of the thermal management system is much smaller with the PCM than without it, even though that PCM itself can have some mass. So what I'll talk about today is really three things. The first is a system-level modeling approach for capturing dynamics of thermal management systems that include phase change materials and thermal energy storage. Then we'll design a control approach that addresses some of the key dynamic challenges with these systems. And then we'll do a simulation example to show how effective this controller is. So the candidate thermal management system that we're going to study is shown in the top right of this figure, generally representative of architectures we might see in a lot of vehicle systems. What we have here is a single-phase fluid stored in a tank and pumped through two parallel passes. In each, there's a heat load applied to a cold plate. So this red arrow would represent the heat generated by some electronic device. We then flow through a PCM material, or can use a valve to bypass that flow through the PCM, junction back together, and go through a heat exchanger that rejects energy to the ambient environment. One of the key challenges we run into with a system like this is that the dynamics span a wide range of timescales. And so I'll talk more about the model in a second. However, what we see by analyzing that model is that timescales can span 4 orders of magnitude. We look at something like the eigenvalues of a linearization. So we have a really wide range of time constants over which these dynamics can evolve. And the reason that is because we have this phase change material that can store a significant amount of thermal energy, as well as some ability to store thermal energy in the tank. So that'll create slow thermodynamics. Then we have somewhat faster thermodynamics of the wall material, of the cold plates, and our heat exchanger. And then we have very small thermal capacitance, fast dynamics in things like our fluid pipes. We also have a real challenge with these systems in that there are several different types of nonlinearities that can occur. One of them is the actual dynamics of the PCM material itself. And for this, we can look at a fairly common model used for system-level modeling of PCM. It's been used over the last 30 years or so, wherein we'll lump this entire PCM module as a single state, and that state will be the state of charge or solid fraction of the PCM material. And we can write the differential equation for this state as a function of the thermal capacitance of the PCM module, the mass flow rate of the fluid, the CP of the fluid, the inlet temperature of the fluid flowing through the PCM module, the melt temperature of the PCM module, and lastly, this coefficient, which will be a heat transfer effectiveness coefficient. And if we look at these curves, right, what we see is that this coefficient is a function both of the current state of charge of the PCM module and the sign of the temperature gradient, which tells us whether the module is being solidified or melted, or in the terminology I'll use here, charged or discharged. In addition, all of the fluid flows of the system incur nonlinearities in that we're multiplying mass flow rates, which are our input, it's chosen by our control decisions for the pumps and valves, multiplied by states of our systems and the temperatures. And so I'm highlighting the tank here for the case where the mass flow into the tank is equal to the mass flow out of the tank. But this is true, for every advective heat transfer within the system. And then lastly, to have some kind of variety in our model, we're going to treat V1 and V2 here as solenoid valves. So they're switched actuators. We'll treat V3 as a continuously variable valve, really just so that we have some of both in this candidate system. But specifically with these switched valves, what we see is that the operating envelope for the mass flow rate through the system changes as a function of what these valve positions are. Specifically, if we bypass one of our PCM tanks, that reduces the pressure hydraulic resistance, I should say, in the line, and therefore allows us to achieve greater mass flow rates through some lines. So there's maybe this trade-off over, do we want to have a high rate of flow in our system, or do we want to flow through our PCM module? To capture all of these different types of nonlinearities, we'll use the graph-based modeling approach shown here. We've published a fair amount on this in the past. The key new contribution, I'd say, is we've shown that this specific model of a PCM module can be incorporated inherently into the graph-based modeling approach. And essentially how this works is that we apply energy conservation over all of our states, which are, in this case, either temperatures or the PCM state of charge, and all of the nonlinearities get pushed into these functions that capture the transfer rate of energy between states. So each of these lines here connecting to vertices is one of these power flows that could potentially be nonlinear. We can stack all these equations together, again, to isolate our linear part of our dynamics and the nonlinear equations that govern these power flows. So for this system, we'll design a two-level MPC controller with a logic and PI-based controller underneath. And the idea of using this hierarchical approach, or some folks might think of it as a cascaded approach, is to address the multi-timescale behavior of these systems so that we can plan long-term behavior in our upper level, have that controller update relatively slow so that we can predict a long time into the future for a given number of steps in our MPC horizon, and use that to really govern the slow dynamics like the tank temperature and the PCM state of charge. And then at the lower level controller, we'll plan for short-term transient behavior of the system. So this would be more like governing the wall temperature of the cold plates and the heat exchanger, as well as some of those temperatures of the pipes. This will try to track the long-term behavior desired by the upper level while rejecting some of the model error and disturbances that can come from using a slow update rate at that upper level. And then at the bottom, we'll compensate for actuator dynamics with some classical controllers. So in that upper level controller, we really want to capture the long-term behavior of the system, and performing a single linearization wouldn't necessarily do that, because if our, for example, our state of charge of a PCM tank changes significantly within the horizon, that could mean that our linearized model of some of those nonlinearities are not accurate. So what we do in this level is we discretize across the operating region, both in terms of the mass flow rates achievable, and that's all of these large black circles are different mass flow rates that we chose as discrete operating points. And we also discretize over heat transfer effectiveness values for each PCM. And then we build a model corresponding to each of these operating conditions and combinations of operating conditions. And each of those models is embedded in our MPC controller as a mode that we can select from. So for example, if we're in a particular state of charge region in each phase change material and a particular mass flow rate, that combination might define one mode of our system. Here's the set of constraints and objectives for that MPC formulation. This is a mixed integer quadratic program, MIQP. I won't go through it in detail. The details are in the paper. But what I want to point out is that we have essentially if-then cases for each of these types of nonlinearities. Right? So whether we're charging or discharging PCM, the value of the heat transfer effectiveness under charging and discharging, and the mode mass flow rate constraints with the valve switching are also embedded in here. So these nonlinearities are approximated using switching. At the lower level, we really just need a model that's accurate over a short period of time. And we want a model that can be solved quickly. So having many modes in our MIQP wouldn't necessarily be feasible for real-time implementation. So what we do here is we linearize locally about the current operating condition, with the exception that we include models both for charging and discharging of each PCM, so that if our temperature gradients flip, our model will be accurate. We found that this approximation of the dynamics gives sufficient accuracy over the horizon of this lower level controller to allow us to make good decisions about how to govern our system, how to move thermal energy around, and choose actuators. Here's a result showing the performance of this controller. I'm going to talk mostly here about the performance for this PCM1 loop. And of course, there are results for PCM2, which is operating simultaneously in the paper that can be explored there. So this upper subplot is showing the heat loads applied to the system. If I go to the next slide, you'll see that what we have here is really a very fast pulsing. The lower level sees this pulsing. Because the upper level is updating more slowly, it just sees the average value of that pulse over its update interval. The second subplot is showing the mass flow rates. And every time we have one of these vertical lines, that's showing a switch of either valve 1 or valve 2. And I'll point out that the plots here, the switching decisions, are highly coupled to what is happening in PCM2. And we might choose to bypass PCM1 so that we get a higher rate of flow in the system to be able to cool cold plate 2 better. So this is where, even though we have a distributed cooling system, there is still coupling of one line to the next. In this third subplot, we see our temperatures. You can see there's this slow, rather slow transient, but if we zoom in, we see that there are also much faster transients that are caused by the switching of the heat load. And we can see that we're able to successfully regulate this very closely within our constraints, showing that that lower level controller is doing a good job of compensating for the difference between this fast pulsing that's really happening to the system and the approximation of that the upper level controller receives over its slow update rate. And then lastly, this subplot at the bottom shows our PCM state of charge. And what I want to highlight is that in this period of time during which there's no heat load applied, our upper level controller commands the system to charge up this PCM. Now this isn't necessarily the most efficient thing in isolation if we were to look at that time, because we're using our pump, right, to cool the system when there are no states near their temperature limits. However, what our controller is doing very intelligently is building up some thermal storage in our PCM so that during this second period of high loading, when we know this temperature is going to spike, we have the ability to cool that off. Right? And again, this temperature doesn't achieve its upper bound, but that's somewhat due to coupling with the other loop of the system, right, which is also at this time getting rather hot. So with that, I'll summarize very quickly that what this paper covers is, first of all, an approach for modeling at a system level the use of phase change materials within a thermal management system. Then we talked about using a switched or hybrid hierarchical control approach to address some of the specific challenges to systems like this, which are the multi-timescale behavior and the nonlinearities that are found in the model. And then lastly, we showed through simulation that the results are quite promising, and of course we'd like to extend this to experiments in the near future. And with that, I'd like to take any questions that folks have. Thank you.